Welcome to the Data Center Design Considerations course. The purpose of this unit is to equip you with the basic knowledge to understand the main data center requirements and how they can be fulfilled. We'll start with defining what is a network topology and what are the considerations when choosing the right topology for one's needs. Then we'll present two design approaches: the hierarchical network design, that is considered the traditional design, and the leaf spine used in modern data centers. Later, we'll compare Layer 2 versus Layer 3 designs and understand how their behavior and protocols impact network performance. Let's start with an overview of general data center design considerations. A data center is a facility used to house computer systems and associated components, such as compute, network, and storage systems. A data center can be the size of a small server room to a few buildings geographically distributed. The data center is a critical business asset where companies run their workloads. The modern data center has evolved from a facility containing an on-premises infrastructure to one that connects on-premises systems with cloud infrastructures where networks, applications, and workloads are virtualized in multiple private and public clouds. Data centers require scalability, resiliency, and security. The modern data center is also becoming more technologically advanced to provide better efficiency. Data center design is the process of planning all of a data center's essential computational and non-computational parameters. Some are listed here: number and type of required servers, network layout, power, cooling, and ventilation systems, physical data center security, disaster recovery, and business continuity planning. Modern data center design will incorporate many different aspects that will make it easy to manage and more efficient. We won't cover in this unit all data center design aspects, but we will focus on networking considerations. One important design aspect is the network layout or topology. A network topology is the schematic arrangement of elements, such as links and nodes, which ultimately constitutes the structure of the network. It describes not just how devices on the network are connected, but also how data moves from one node to another. The following are key considerations when choosing a network topology. Availability. Enterprises that run critical applications need maximum availability of their network resources. High availability features must be considered throughout the network. Hardware and software, network protocols, as well as environmental and power features all contribute to the overall availability of the network. Reliability. In many of the industries, even brief downtime and delays are unacceptable. For this reason, network reliability is a fundamental consideration. Performance. The topology of a network is key to determining its performance. Choosing the right topology can increase performance while making it easier to locate faults, troubleshoot errors, and more effectively allocate resources across the network. Future growth. If the network is expected to grow in size in the mid to long term, choose a network topology that's easy to add new nodes without negatively affecting performance or the user experience. Budget. You can choose a topology that is perfectly suited to your needs, but it may not be affordable. There will probably be a lower priced alternative that's nearly as effective. The hierarchical design separates a network into distinct layers, where each layer has its role in the network. This hierarchical network design is most effective for north-south traffic patterns, where a majority of the data goes in and out of the data center, such as client-server applications. The model scales somewhat well because of its modularity, but may be subject to bottlenecks if uplinks between layers are oversubscribed. Cloud computing, virtualization, big data, and related trends have come together to transform data centers. Modern data center environments are becoming much more dependent on east-west traffic, as more data moves between servers and storage nodes in order to meet end-user demands. The network design needs to serve the modern data center's increasing demand for server-to-server communication, scalability, and resiliency. In the past few years, many data centers have transitioned to a leaf spine design to overcome the limitations of the hierarchical design. A leaf spine architecture is a two-layer full mesh topology composed of a leaf layer and a spine layer. The spine switches connect the leaf switches with one another, whereas the leaf switches connect servers to the network. For that reason, the leaf switches are also referred to as the top of the rack switches, or TORs. Every leaf switch is connected to every spine switch, and obviously vice versa. The leaf spine architecture has many advantages as listed here. If the network reaches a certain scale, a third level of switches should be considered. In this case, the upmost level, called the superspine or core, is used to interconnect the spine switches. But yet the same rules apply. Now that we know that the leaf spine design is the best choice for modern data centers, let's see whether the network should be configured to operate at layer 2 or layer 3. We'll start with layer 2. In a layer 2 network, networking devices are configured for switching, meaning they make layer 2 forwarding decisions. They build and maintain a MAC address table that maps MAC addresses to exit ports. The switches process Ethernet frames and forward them based on the destination MAC address that is matched against the MAC address table. Overall, a layer 2 network does not scale well and provides lower bandwidth and performance than a layer 3 network. Also, it's harder to achieve redundancy and multipath support. We'll explore the reasons for that in the following slides. Let's focus on redundancy and multipath support. A redundant network design allows for network availability by duplicating elements such as switches or links, so that if an element fails, critical applications are not disrupted. Redundancy attempts to eliminate any single point of failure in the network. In this example, each leaf switch has a link to each of the spine switches, so that there are two available paths for the host to communicate. Let's assume that when host A communicates with host C, the path is via spine 1. But what happens if the link between leaf 1 and spine 1 fails? There is another available path via spine 2 that can now be used for traffic forwarding. This is the idea of a redundant network design. There is an active path and a backup path. If the active path fails, the backup path takes over. But if there are two available paths, why not use them both at the same time? This will allow for load balancing the traffic, hence providing twice the bandwidth and better resource utilization. This is the advantage of multipath support. Multipath is a strategy where traffic forwarding to a single destination can occur over multiple paths. It can substantially increase bandwidth by load balancing traffic over multiple paths. However, it may be difficult to deploy it, especially in a layer 2 network. Let's examine the reason for that. We already know that a redundant network design requires additional redundant layer 2 links to provide a backup path in case of a link or switch failure. Those redundant links allow multiple paths between a pair of nodes. Well, that sounds terrific because that's exactly what we're trying to achieve. But because of the behavior of layer 2 networks, this creates a layer 2 loop that eventually results in traffic denial. Let's see how it's caused. You probably recall from the previous unit how broadcast frames are handled by the switches. They are flooded in the network. If there are loops in the network, the broadcast frames circulate endlessly in the network, consuming all available bandwidth. This phenomena is called a broadcast storm, and it must be avoided. Otherwise, bandwidth is unavailable for normal network traffic. So, the simple conclusion is that a redundant layer 2 network design causes broadcast storms. Does that mean we can't have a redundant layer 2 network? Not exactly. We can and should have a redundant physical design, but logically there can only be one active path at a time between any pair of end nodes. We'll now present the protocol that provides this capability. Spanning Tree Protocol, or STP, ensures a loop-free logical topology for Ethernet networks. It allows a network design that includes redundant links and provides automatic backup paths if an active link fails. STP achieves that by identifying redundant links and putting the redundant ports in blocking state. Then, when a topology change occurs, STP reacts and moves blocked ports to forwarding state. It is important to mention that the convergence time of STP is between 30 to 50 seconds, during which data traffic is not served. Maybe this convergence time was acceptable in the 1980s when STP was initially developed, but no modern data center can tolerate such a long convergence time. Rapid Spanning Tree Protocol, or RSTP, was introduced in the 1990s to provide rapid recovery after a topology change. There are different enhancements to support faster convergence, and we won't discuss the details here. In general, RSTP allows the switches to almost immediately react to a topology change and start negotiating port states. In addition, RSTP provides alternate ports that immediately move to forwarding state if a port becomes unavailable. This and more allow RSTP to respond to changes within a few seconds or as fast as a few milliseconds on a physical link failure. To summarize, both STP and RSTP allow a redundant network design by providing a single active path at a time. The backup paths are not used at all as long as the network is stable, and the additional bandwidth is wasted due to blocked ports. In order to allow a Layer 2 network design to provide multipath support, a third version of STP was introduced. Multiple Spanning Tree, or MST, enables configuring multiple STP instances with a group of VLANs mapped to each instance. MSTP settings can be configured so that each instance has a different active path. In our example, the green path is the active one for VLANs 1 through 50, and the purple path is the active path for VLANs 51 through 100. When hosts A and C in VLAN 2 communicate, the traffic will take the green path via spine 1, but when hosts B and D in VLAN 68 communicate, the traffic will take the purple path via spine 2. In this way, we achieve load balancing and multipath support, hence better overall network utilization. Sounds awesome, but in practice, as the network scales, it becomes very difficult to manage multiple MST instances. Another Layer 2 feature to achieve higher bandwidth, load balancing, and redundancy is a link aggregation group, or LAG. LAG, also known as port channel or bonding, enables the aggregation of multiple physical ports into one logical port. The benefits of link aggregation include the following. Higher bandwidth. LAG provides the bandwidth that is the sum of the physical link's bandwidth. Load balancing. Traffic is distributed on all physical links, which are part of the LAG. High availability. When a physical link fails, other links of the LAG continue to serve the traffic. While LAG provides aggregation of physical links that reside on the same switch, multi-chassis LAG or MLAG allows for the aggregation of the physical ports of two separate switches into one logical port. MLAG switches appear as a single Layer 2 switch. The dual connected device, host, or switch runs a standard LAG and is unaware of the fact that its LAG is connected to two separate switches. MLAG provides high bandwidth and load balancing, high availability in case of link failure, and high availability in case of switch failure or switch software upgrade. Let's now summarize what we've learned about a full Layer 2 network design. We need to configure MSTP for multipath support and MLAG for redundancy. While it may be a simple design, well understood and easy to configure on a small scale, Layer 2 protocols are difficult to manage at scale. The design may be suitable for traditional enterprises with few network needs. The conclusion is that for scale-out modern data centers, a Layer 3 design would be more suitable. Let's now explore the reasons for that. In a Layer 3 network design, routers or Layer 3 switches are configured for routing. If you recall from previous units, routers build and maintain a forwarding database called a routing table that maps remote IP networks to next hop routers. The routing table is populated by configuring static routes or by enabling a dynamic routing protocol such as OSPF or BGP that will be introduced later. Routers then forward IP packets to their destination based on the routing table entries. Achieving load balancing and multipath support in a Layer 2 design is very difficult. It involves a combination of STP and MLAG settings that are hard to maintain in large networks. In a Layer 3 design, it's much easier since routing protocols have built-in mechanisms for identifying and eliminating routing loops. Thus, a Layer 3 design provides redundant active-active links with no blocked ports. Routing protocols also support equal cost multipath, or ECMP. ECMP is a routing strategy that allows packet forwarding to a single destination over multiple best paths. In addition to that, IP packets carry a time to live, or TTL field, that is used to avoid packets endlessly circulating in a loop. If an IP packet ends up in a routing loop, it can traverse 255 hops, or routers, at most, before it is discarded. When choosing a routing protocol to be used in the data center, there aren't too many options to begin with. Preferably, an open standard, scalable, and robust protocol should be chosen. When comparing the two most commonly deployed routing protocols, OSPF and BGP, BGP is the routing protocol of choice in modern data centers. We won't go into the details of these protocols, yet we will highlight some properties in favor of BGP. BGP is the routing protocol that makes the internet work. BGP allows service providers to exchange routing and reachability information so that packets are routed on the internet. It is designed for scalability and stability in very large networks. BGP is an increasingly popular protocol for use in the data center, as it lends itself well to the rich interconnections in a leaf-spine topology. The following are some notable BGP properties. BGP does not require a routing state to be periodically refreshed, unlike OSPF. It has many robust vendor implementations. BGP is a thoroughly tried and tested protocol that comes with years of operational experience. Now that we're convinced that a Layer 3 network design is more suitable for our high-demanding scaled-up modern data center, let's see two design options. The first one would be a combined Layer 2, Layer 3 design. Here, the leaf, Tor switches, operate at Layer 2 towards the nodes with MLAG for redundancy. The uplinks from leaf towards the spine switches operate at Layer 3 with ECMP to provide scalability, redundancy, and load balancing. These designs are simple, well understood, and easy to configure, but still use Layer 2. Typical deployments would be data centers and big enterprises, high-scale bare metal hosts, high-scale virtualized hosts. The second option would be a full Layer 3 from host to leaf spine with routing and ECMP for redundancy even at the host level. A very high level of scalability and redundancy is provided, and we've eliminated the need for Layer 2 protocols. One drawback is that it may somewhat complicate host administration since it requires a routing protocol to run on the hosts, also referred to as routing on the host. Typical deployments for this design would be a highly virtualized environment with a high degree of host mobility. We've completed the unit. Thank you for watching.